Okay, so last lecture we discussed thermodynamics of learning when the system was when the trainable variables were fixed and the non-trainable variables acquired equilibrium state. We discussed how that should be done, and actually in the last two previous lectures we did that. Now, I also mentioned that you can also treat trainable variables thermodynamically, and then you would have to include new phenomenological parameters such as the entropy of the trainable variables, number of trainable variables into your phenomenological description. Now we're going to take a little step back and say, all right, let's separate the scales. Let's have all the trainable, non-trainable variables thermalized, and the trainable variables are dynamical. And we're going to study the dynamics of them, not individually, but at the level of probability distributions. So you can think about this as a non-equilibrium dynamics of the trainable variables. Now, eventually they'll equilibrate, and then if you average this dynamics over large time scales, you would get an equilibrium description. But here we're interested more fine-grained descriptions of the trainable variables. Now, the setup is here. You have trainable variables that I denote by Q. So I combine all of the weights and biases in a single vector notation Q. And then the non-trainable variables, X, I will be treating at the level of ensembles. Now, here I start calling them hidden variables for the reason that will become clear shortly. For now, think about them as non-trainable variables. Another important thing is that it might happen that your neural network is very large, and many even trainable variables do not learn anything, and they behave stochastically. And then at that point, you may want to integrate them out as well and also treat them at the level of the ensembles. And so, and all of those variables are just going to call the hidden variables X. Or non-trainable variables X. Okay, now what are the dynamical evolutions? What are the dynamical equations that describe the dynamics? There'll be two. One is just a chain rule here. We have written that how does the free energy of non-trainable variables, of those hidden variables, changes with time. This is the very same F free energy we were talking 2 lectures ago and last lecture as well. Now, it depends on 2 parameters, on T and on Q, okay? Now, and so to find the full derivative, you basically differentiate with respect to Q, T, and then you differentiate with respect to Q, where Q itself can change with T. Now, remember, Qs are our trainable parameters. And so in a stochastic gradient descent, we know how they change. And in the statistical description, what they do, they're trying to drift in the direction of the extrema of the free energy. Whether minima or maxima is not important, but once they drift there, they stay there and they no longer move. And so this is an equation that describes the stochastic gradient descent nature of the evolution. Okay, good. So, and then we can just substitute dq dt here to get that final expression of how the free energy of those non-trainable variables, of those hidden variables, would change. All right, that's one equation. And then this equation is equation for F for the free energy. Now, the second equation is a diffusion equation or Fokker-Planck equation that tells you how the probability distribution over trainable variables changes with time. So you can to understand what this is, you can imagine many computers that are all running the same simulation with the very same training data, but there is a stochasticity, there is a different random seed, and so they all evolve differently. And then after they run for some time, you can collect a distribution of the trainable parameters of the weights and biases, and you can study how that distribution will change. You can run all of them in parallel on the computers, or you can do it one by one. You run one simulation, then you run another, run the third, and so forth. Now, of course, in reality, we only run it once, but treating it as a probability distribution tells us how things change. And so if we can affect how this probability distribution changes, we may make the learning dynamics be more efficient. All right, so now the first line is nothing, is the standard Fokker-Planck equation, where this drift, so whether the two terms, one term is from diffusion, like random walk. Basically, the Q can be kicked to left or right randomly, and the length scale on which it gets kicked depends on this D, which is called the diffusion coefficient. We'll discuss how that diffusion coefficient depends on other things later. The other term is a classical drift. I'll call it a classical drift. Basically, it tells you that the trainable variables are not random, and they do evolve in the direction that extremizes the free energy. And so this is the very same equation that should be plugged here, and then you get that result. So two equations: one, how the free energy of non-trainable or hidden variables change, and how the trainable variables change. Now, the reason why hidden is appropriate, again, you will see later, but for now it is something that we don't pay close attention to. We only think about them at the level of ensembles. However, for Qs, for the trainable variables, for biases and weights, we pay a lot closer attention. Okay, so that is the setup. Any questions about the two equations?
Can you explain the difference between the d by dt on the left and partial df by partial dt?
Which equation is this?
The first one.
The first one.
Yeah.
df dt and partial df dq?
The d by dt on the left, and then the partial df by dt.
Oh, okay. On the left, it's a full derivative.
Okay, got it.
So it tells you how does this whole thing changes with time. On the left, well, it changes two different ways. It changes through t explicitly, and implicitly through q. That's all.
Okay, got it.
All right. Other questions? So at this point, there is you can think about this as, again, as a chain rule. There is no assumptions here. This is an assumption of diffusion, and this is an assumption of the stochastic gradient descent. So really, very not very strict assumptions at all. We are thinking about probability distribution, and that's kind of what makes it non-equilibrium. This non-equilibrium comes, we are looking to see how this probability distribution changes with time. In the equilibrium, this derivative would be zero. It would stop changing with time, and then we would have a solution. What would probability distribution look like in the equilibrium? But here it's a non-equilibrium, so we are really trying to see the process of approaching there. Okay, now the one important comment to make here. Well, the first important comment that you see that dynamics for P and F are coupled. So yes, in the diffusion equation, usually what you have F predetermined, so it has no time dependence, and then you solve it, and then you obtain your equilibrium distribution. Here you have a coupled distribution, so really the dynamics of F affects P, and then both of them are the coupled equation. And that's what I say here. In the optimization problem, F is usually primary. You solve for that first. You find it first. And then P is secondary. And then you solve for the P on the non-changing F. Now here we can do better than that. We have to solve for both of them. And so the proposal that is often used in the non-equilibrium thermodynamics is that some kind of stationary entropy production principle should be satisfied. Now note, before we were using maximum entropy principle, there were no time evolution. We were saying what would be the distribution, the most probable distribution when there is no time. Here, this principle is for the evolution. And so we are not asking about what would be a state, time-independent state in the equilibrium, but what kind of paths the learning system would take. Paths for both P and for F. So how would P change with time and how would F change with time? And the claim here is the following, that the path taken by a learning system, but a good learning system, and the one for which the entropy production is stationary. And here I'd like to pause and draw a connection to the well-known Occam's razor principle. Basically, what it tells you is that if you're constructing a system and you want it to be an efficient learner, then you should make sure that it uses least possible number of trainable variables to memorize whatever data set it has, so that the rest of the other trainable variables are useful to memorizing something additional, either for that data set or for some new data set. And that's what we call the Occam's razor principle. If we construct theories, we are trying to come up with a theory that has fewer parameters. And by doing that, that frees out to us the ability to develop theory further with other parameters that would be describing more fine-grained description of the system or some other phenomenon. And so this is well-known Occam's razor principle. Here just tells, like, whatever the system is going to take, make sure it takes the path that extremizes the entropy production. So in the relation of Occam's razor, you want to minimize the entropy destruction. You want to have lots of entropy in the trainable variables. The more it will get destroyed, because eventually there are fewer solutions than there are all possible states, and so the system will kind of go to some states corresponding to the trainable variables. But you want to make sure that it goes it in a way such there are more and more solutions are available. And the more solutions are available, the more entropy in the trainable variables are, the better chances you have in finding a solution. Maybe not a perfect one, but a decent one. Okay, so now let's write formulas. Now I will write this formula without showing the details how to go to this formula, and you should be able to do it yourself from this expression. From the diffusion equation, for the Fokker-Planck equation. What I have here is I just plot the change in the entropy with respect to time, where entropy is a Shannon entropy, just like what we had before, but for now trainable variables. Okay, so it's a minus integral of P of Q log P dQ, right? So this is a Shannon entropy. And now you differentiate it through derivative goes inside the integral, and then you basically use this formula to express how the entropy changes. And there will be two terms. The one term is a stochastic term, so you see this diffusion coefficient appearing here, and it will just tell you how the entropy is produced from the random walk, right? So the and the other one is a destruction, entropy destruction form. It tells you how the entropy is destroyed through learning as the system approaches to some fixed points of the free energy. Now, I will make an assumption that there is no second term, and this one dominates everything. This assumption is not crucial at all. And in this paper, it was shown, it was paper about something else, but it was shown that even if you keep this other term, with a proper redefinition of F, you can, everything I'm about to say will be exactly correct. Basically, it has to do with just completing the square and then redefining the certain shift for the free energy, not important. Okay, so very good. So we have entropy production, and we have a principle that says that the learning system must take a path for which entropy production is stationary. Now, that's a principle, but it has to respect all of the constraints. And the only constraints we have is that the free energy has to evolve in a certain way. And so that puts us into the position of setting up a variational problem, just like what we had before, right? It's a method of, again, the method of Lagrange multipliers. Before we had a term for the entropy, and the constraint imposed by the average loss function. Now we have a term for the entropy production and another term which is a constraint on the equation for the evolution of the free energy. So we want the free energy not to disappear and satisfy the equations which we wrote. Okay, so then you set up those two terms. Now you have a new Lagrange multipliers. Remember, before we had beta. Now I'll call it lambda. You should do it. You should write it. The only now difference from what we had before is before we had a constraint on the average loss. Now we have a constraint on this V, on the average free energy production. Other than that, the setup of the problem, all the variational things you do are very similar. Yes, there is one more integral. So before we had integral over only some variables, or variables x. Now you'll have also integral over time. And that is because you're trying to solve the problem not just for p as a distribution over some variables, but also p as a function of time. So it's a probability distribution that evolves with time. Now you can use the differentiation by parts to move things around and put it into this form. This form is most useful for us. Basically, you had a square root of p on the left, you have a square root of p on the right, and then you have some operator here. In fact, this is exactly the form in which I put. You can even start, first for starters, start with this first term and see how that can be put into that term. Basically, you have some derivative with respect to p here, you have some derivative with respect to p here, and even before that, you can start with your definition of Shannon entropy that will take you here. So make sure you know how to do these steps, and also make sure you know how to do differentiation by parts, how to move the derivative from one p to another p, right? You can move it freely, but then there'll be usually a boundary term, and then if you make an assumption that the probability distribution is vanishing at the boundaries, then it's zero. Or if your boundary are periodic, it's also zero. Anyhow, so that is the expression that you will get. So you'll get some square root of p on the left, square root of the p on the right, and operator inside. Now, what I'm going to do next, and then I'll ask questions, see if you have any questions. I will only rewrite it a little bit. And basically, this rewriting will be equivalent to defining mass as epsilon over 2 gamma, where epsilon is here, and h bar, where h bar is epsilon times square root of 4d divided by gamma lambda. So this is just a definition that would be convenient later, but if you do that, this action function, I'll call it action in quotation marks because it reminds you of action in physics, although it is just a function, a functional for the two paths, two functions, p as a function of q and t, f as a function of q and t, and lambda, just a number. Okay, are there any questions?
Does time symmetry make sense in this case? Like, if you change t to 2 minus t, does anything follow from it?
If you change t to what?
2 minus t.
Oh, the direction of time symmetry. Of course, you don't have it initially. That's actually a very good question, extremely good questions, because originally in your problem, you do not have time symmetry. And you have a preferred time direction where the entropy is mostly produced. But once you start getting closer and closer to equilibrium, then as we will see, this time direction symmetry will emerge. I keep hearing sound on the background. I don't know if somebody hasn't unmuted himself. Please mute unless you have a question.
I have a question. I'm just having a really hard time seeing where you got, like, where is U? I mean, I know we have the equation, F equals U minus TS, but what is U? What's the equation for U? I was just trying to follow along with the math.
We don't have U here, right?
Okay, so then how do we find
So
F?
U is sitting inside of the free energy.
Okay,
So U may mean loss function, right? So the only okay, so I mentioned U here.
right.
Okay? So once you have U, you can take a Legendre transform from last lecture, U as a function
Right.
of S, and to find F. Now you have F. That's one way to find F.
Okay.
The other way to find F is just this. Again, you have some, this Z is an integral. It's an integral over,
Right.
and then you take a log of, you first take this integral. It's very hard to take usually. In the quadratic limit, we know how to do that. And then what you find this log, and then this is what F, this is the free energy.
Okay.
But at that point on, you only work with free energies. You don't, at this point, your like free energy is more appropriate in this. So it's like, what is the state the system is in? If you know exactly your loss function, then it's like you know exactly your energy. It's called the microcanonical ensemble. And then you should use it. If your energy fluctuates, and there is some average energy, then it more appropriate ensemble, which is what U is the average energy, average loss function. That the more appropriate ensemble is canonical ensemble, and then F is the relevant quantity. F is what the system tries to extremize. That's what I mean by it. So it's kind of, it finds a balance between loss and the entropy, if you will.
So where did the S come from on the next slide? The derivative with S?
So this one, yeah. So this is a new S. So this is S.
Oh, okay, because you said
new S.
I thought you said
Yeah. No, it's a very good point. It's a very important good point. So now up to this point, I was not even having any subscript to S. There was only one S, and there was a reason for that. I didn't want to confuse you right away. Now, but you have to understand that S was just the entropy of the non-trainable variables. And this is not all. There are also trainable variables. So it only makes sense for us to consider non-trainable variables and forget for trainable if we freeze the training, if we are only looking how the network evolves without training. Once you have training variables, there is this another parameter that you have absolutely must include, and that's the entropy of the trainable variables. And today's whole lecture is about that, is about how would the trainable variables evolve. What tells us how they will evolve, what kind of equations they would be governed by. But it's a good question. Okay, other question. And I understand this is heavy. So now it's heavy if you haven't done any variational problems before. We had done it. 2 lectures ago, we discussed how to use the method of Lagrange multipliers, but our task was a bit different. We wanted to find a probability distribution given a constraint on the average loss. Here, we're doing a similar, but instead of probability distribution, we want to find a probability distribution trajectory, probability distribution which changes with time. Okay, so it's more than just a distribution, it's a changing distribution. That's one complication. And the second one, constraint is not on the average loss, but the constraint on the free energy production on this guy. Okay, those are the 2 differences. But then the logic follows. We still have this one functional to extremize, and we still have the parameters P, F, and lambda, with respect to which we would have to vary this action. I call it action is just because it's analogous to action in physics, but you should think about this as a functional that is being extremized. Other questions?
Yeah, I have a question for the principle of stationary entropy production. Yeah, this one. So you said that an optimal or more close to optimal network will not very quickly decrease entropy.
Of trainable variables, yes.
Yeah, so I mean that makes a lot of intuitive sense, but I'm wondering if has there been any like numerical experiments confirming that or showing that?
Right, good question. So first of all, it is just a principle, so really it has to be tested one by one to see whether this is correct. Now, there were not many numerical tests, so there are some people who were doing the testing it, but it was not explicitly proved that this principle is correct. Now, I think what will happen is, and it always happens with all entropy principles, is you try testing them, and if they don't work, usually what it means you haven't included the right constraints, right? Once you include the right constraints, then they start behaving more well. But it's a good project. No, haven't been explored completely, and that is something that should be done, of course. And as like through those lectures, I always list lots of open problems and questions, and that's would be one of them as well.
Thanks.
Sure. Okay, so let's move on. So now that just mathematics. So we set up the problem. We know what our degrees of freedom are. It's P, F, and lambda. We've defined it as functional. We need to just vary it now, everything with respect to P, F, and lambda, vary this functional. And then by setting variations to 0, we'll obtain equations for P and F. That would be okay. So Haley, I think your microphone is not muted, and that's why we keep hearing some noise. Oh, I can mute it. I can just mute myself. Why? Okay, perfect. Okay, so let's keep going. Now we really want to solve this, but before I do that, I'd like to take you through as 3 steps. I'd like to quickly teach you classical physics, quantum physics, and the reason for that is because, as I'll argue, the equations that we obtain from here are very similar to what we have in quantum physics. Not exactly quantum physics, so I do not expect the learning system to behave as a quantum system, but I think I do know how it may start behaving that way. Okay, so let's go through this. And again, as I understand, most of you do not have physics background, so do not hesitate to ask questions. It's just 2 slides, and after that, I promise you will know more physics than most physics majors. Well, I cannot promise that, but that's the whole. Classical physics in 1 slide. All of the classical physics that we know can be formulated using these 2 principles, 2 postulates. One is what is the state space, and the other one, what is the dynamics. Now, the state space of a classical system is described by a vector in an even dimensional space. Always even dimensional space. We can discuss why that's the case, but all of the classical system seems to work that way. So intuitively, you might have remember from your physics undergraduate classes or even high school classes that to describe an object, you have to specify its location and then velocity, right? So 3 numbers for a 3-dimensional location, 3 numbers for the 3-dimensional velocity. And so it always comes in pairs. There are always an even number of them. Okay, so even number of variables. Great. And then there is the evolution postulate. Evolution postulate says that out of all of those even number of variables, there is a function of those variables. This function is the main object in classical physics. It's called the Hamiltonian function. And the space of all those points is called the phase space. So that's why the first is the phase space postulate. The other one is evolution postulate. Okay, so given this Hamiltonian function, we know exactly how Q's and P's will change. And the interesting property that comes from this second postulate is that they come in conjugate pairs. So Q1 tells P1 how to change, and others also contribute, and Q2 and P1 tells Q1 how to change, and others contribute in those 2 sets of equations. So basically, to figure out how Pi changes, dot means dpi dt. You have to find the partial derivative of h with respect to qi. Now, of course, this doesn't tell you that this right-hand side would only depend on qi. It will depend on all others because this function, it may depend on all others because this function is a function of all those variables. Now, the same for qi. The only difference is this minus sign. You have minus sign in one case and no minus sign in the other case. It has to do with the symplectic structure imposed on the phase space. We're not going to go into details on that, but it's a very elegant and interesting mathematics that arises there. All right, so you have a state space and you have evolution. If you know where you started, you know exactly where things will go. There are no probabilities attached. It's a completely deterministic system. Now, even the phase space volume, there is a Langevin equation that tells you that space volume would always be constant, meaning you can, like, if you start not with a point, but with a ball of initial conditions, then it may squeeze and stretch in one direction and squeeze in the other direction. And but the volume of this as it moves through the phase space will remain constant. All right, the best thing to do when you start to study is to consider an example. So this is the simplest non-trivial example, which is called a classical harmonic oscillator. It's only when you have phase space of only two-dimensional phase space. 2 is even, so we're good. 1 is q, 1 is p, and the function is p squared divided by 2m plus q squared divided by 2. What's important, it's quadratic in p and it's quadratic in q. That's the simplest setup. Now, and then you just use this equation and say, well, p dot has to be a partial derivative of h with respect to q. So you differentiate it with respect to q, you get kq, and then there is a minus sign, minus kq. Now, q dot has to be a partial derivative of h with respect to p. You do the same. 2 jumps on front, cancel with this 2, you have p over m. So these are the two equations. Now, p dot equals minus kq, q dot equals p to the divided by m. Now you can combine those two first order differential equations into one second order differential equation by taking a second derivative of the second equation. Basically, q double dot will be p dot divided by m. M doesn't change with time. It is just not a dynamical parameter. And then once you have p dot here, you can substitute the other thing, the other equation, and obtain the second order differential equation. So basically, you got rid of p here, you have only q, but now it's a second order. So you really, to solve the boundary initial value problem, you need two data for q and q dot. The solutions would be sinusoidal waves. And that's what harmonic oscillator is. It's basically oscillates about some mean value. All right, so that's classical physics. Again, nothing fancy here, although I do want to argue that the most interesting and fun mathematical part happens in this Hamiltonian and the symplectic structure that comes with the phase space portion, with the phase space. All right, now let's move to something a bit more advanced in terms of less, meaning that fewer people actually study it, and it's a quantum physics. Again, one slide of all of the quantum physics. This was one slide of all the classical physics, and all of the classical physics is like that. Now, this number can be very large, this h can be complicated, and the same here, but it is like that. Now, quantum physics is all like this. Now, instead of 2 postulates, now we actually have 3 postulates, and that's very important too. The first one is the Hilbert space postulate. Now, instead of saying that we have a collection of, we'll have phase space, now we have a Hilbert space. Now, Hilbert space consists of, in this example, of functions on the very same variables q's that were on the previous slide. But you can really think about this as a vector space, which has inner product structure in it. Okay, So now your state is not described by a even number of variables, but by functions of those variables, of half of them, of q's. Evolution postulate. So this is your state space. It's a vector. How does that vector evolve? And the evolution is described by this equation. This is called the Schrodinger equation. On the left side, you have a time derivative of this vector. Of this, in this case, it's a function. The reason why I say vector function interchangeably is because square integrable functions form a vector space. It's infinite dimensional space with L2 norm defined as an inner product, right? So you have two functions, phi and psi. Phi star psi integrated over the range is how we define the inner product. Okay, so functions, and this is how the functions change, or a vector, and this is how the vector will change. A key object is again played by this h. H is a function now of q, that was just a variable. And look, this is an operator. Okay, so really this whole h becomes an operator that can act on the function. Now, again, I don't want to go into details about discussing what kind of operators are common. Although, here's an example of the operator. Again, for the harmonic oscillator, really the only thing that changed is I replaced p squared from the previous slide to h squared d squared dq squared. So this is the only thing that changes. So now it becomes not a function, but an operator. Okay, but the one important point I'm going to spend just a couple of minutes on is that the quantum mechanics does not come just with two postulates. It would be nice, state and evolution. It has to come with a third postulate. That is the source of all of the confusion about quantum mechanics, about all of the debates about the quantum mechanics, about all of the mysteries of quantum mechanics. It turns out that it's not enough to describe a state space as Hilbert space and evolution. You have to give one more ingredient. You have to tell how you're going to observe the system. So in classical system, there was no such questions. They said, all right, this is the evolution. I'm able to measure anything about the system. In Q's and P's, nothing is hidden from me. All of the information is available. Quantum mechanics doesn't come that way. You really have to specify what you're going to measure. So there are so-called measurement operators you have to specify. They have to respect certain conditions. And then there'll be a probability of a given outcome now comes from doing this integral. Again, something we are not going to spend a lot of time on. Maybe if there is one message you want to take from this is there's this third postulate, which is very important. How do you measure things? You might have heard about Schrodinger cat problem. It is related to that. You might have heard about measurement problems. It's all related to that. We will not spend time on that, although the research that we do may shed light in this problem. Before I move on and now turn back to the first part of the lecture, I will want to just present one simple example. This is your system, so it's again described by Hamiltonian, this gate operator, and then you can solve this equation and find a solution. There may be many solutions, but at least one that corresponds to the lowest state. You can take this function, you can plug it into this equation with a Hamiltonian described by this and see that left-hand side is equal to the right-hand side. Okay, good. So classical physics 2 postulate, quantum physics 3 postulate. What's going on with this neural physics? So now we are going to go back to where we spent the first half of the lecture. We're going to go back to this. And we're going to vary with respect to P, F, and get the results. And this is the variation. So if you vary with respect to P and F, you get those two equations. This is the solutions of our optimization problems. They're telling you this is how P should change, and this is how F should change. So here I replaced F with U, but U has this definition. So it's completely specified by F, by the gradient of F. So U is nothing but the gradient of F. So now the reason why I spent last 2 slides explaining what classical and quantum physics, well, it turns out that these equations are well-known equations in quantum physics. They are known the Mondelung equations. They describe how the system evolves, where P can be interpreted as a probability density and U can be interpreted as a velocity of the fluid. And they turn out to be, those 2 equations, equivalent to this equation, which is known as a Schrodinger equation. Okay, so that's fine. But when I say equivalent, the equivalence doesn't go both ways. So they're not completely equivalent. The point is that the solutions of the Mondelung equations, of those 2 equations, solutions that you would get by solving the dynamics of your learning system, are solutions of the equivalent Schrodinger equation. But the opposite is not true. So there are many solutions on this equation, of the Schrodinger equations, that are not the solutions of the Mondelung equation. And so I'll explain you quickly why that's the case before we move on. But the bottom line here is, the main message here is that we do not get from a learning system some kind of quantum behavior. We don't have that. What we get very closely resembling quantum behavior, but not everything of it. Now, the reason why there are solutions in the Schrodinger equations that are not solutions of the Mondelung equation is in this formula. And it is actually very much related to the problem of complexification of the state of neuron that we discussed on the first lecture. Basically, you have here F in the, if we are to move through this equations that we obtain from a relational principle to Schrodinger, then we have to make this identification. We have to make sure that this psi, whatever auxiliary psi or the psi that we want to define, is a combination of both P, which was our degree of freedom for which we were solving, and F. But here F appears in the exponent. Since it appears in the exponent, if I add to this F epsilon over h bar, if I add 2 pi to it, this psi would not change, right? So somehow adding a finite shift to the free energy doesn't do anything with your system. And so the system is equally likely to be in the plus 2 pi state or minus 2 pi or minus 4 pi state. And that's very weird because F has, in our case, an exact interpretation as the free energy of the those non-trainable variables, hidden variables in this case, because they're kind of not, they're outside of our calculations. We integrate over them coarse grain. And that's the problem. It's not a problem from, we can still use this first 2 sets of equations and estimate how the system evolves. But we cannot use the second one, this quantum picture. It is just not going to give us the right answer. Questions, either about classical, quantum, or neural physics. Anything is fine.
So the solutions for the Madelung equations are a subset of the solutions of the Schrodinger equations. Am I understanding that correctly?
That's right. That's those are the solutions where this F doesn't have any discontinuous jumps, because you see this F here for the Schrodinger equation can have discontinuous jumps. It can, for example, you go around and then at some point you just add 2 pi to it just to because this is what you want to have in your solution, and that would be completely fine because Schrodinger equation would not feel it. Any discontinuous changes by 2 pi of this F epsilon of h bar are not noticeable. They're completely smooth with respect to the Schrodinger equation. And so if we restrict ourselves to only Mondelung solutions, we kind of forget about all of the important quantum solutions.
I see.
Okay. Other questions?
Yeah, I have a question.
Okay.
In some contexts, you can use the Mandelung equations to be obtaining some trajectories, as in Bohm mechanics. Do we do something similar in this aspect? Or
Yeah, I mean, you can always use Mandelung equations. There's no doubt about that. It is just restricted. Just you have to make sure that you should not be claiming that, well, I've solved my Mandelung equation, now I know all of the solutions, because you might actually be dealing with a situation where your physical system may be dealing with a situation where it is not a solution of quantum. Let me give you an example, like quantum vertices, right? That would be an example that would not appear as a solution of the Mandelung equations, but it would be easily a solution of the Schrodinger equation. A good point, yes. Okay, so now good and bad news. Well, good news, it doesn't matter. We still have a set of equations to solve, right? Now we can still now run it on the computers, see how things behave, see how probability distribution changes, how the free energy changes, and see whether these equations give a good description. Now, the bad news is that we cannot use a Schrodinger equation, and Schrodinger equation is much simpler. It's a linear equation. There's nothing can be simpler than that, right? You have some operator, a time operator acting on a function or vector, and then you have operator acting on the very same function. So really, we know how to go about solving it. You just find eigenvalues of this operator, and you are done. Then, starting from any initial conditions, you know exactly where psi would evolve. Now, not the case here. Here you have nonlinearities, and you need to be careful about u appearing here and here. You have square root of p appearing here, and so there's no notion. Those are nonlinear equations. No easy way of solving it. Okay, that's so the good news that we have a set of equations. The bad news is it's not so easy to solve and proceed. Now, the second bad news is that, well, maybe we do want to tune our neural network to have it behave according to Schrodinger equation. If we're able to do that, then we can say, all right, so maybe our neural network intrinsically have this quantum dynamics. Yes, we haven't been starting with the quantum equations. We are not dealing on the microscopic scale where the physical quantumness emerges, but maybe we can have an emergent quantumness. And if we do, then we can have a learning system that behaves quantum mechanically. And you've all heard about all this noise about quantum computers one day solving problems that classical cannot solve. Well, okay, so maybe it's hard to build a fundamentally quantum computer, but what not may build an artificially quantum computer, the computer where this quantumness emerges as the level of learning. And now, if we are to tackle that problem, then of course our immediate task is to understand what is it that needs to be done so that this first set of equation becomes the second equation. How can we make this f not to feel the discontinuous jumps, so that the system doesn't really change if you add 2 pi to it, the free energy doesn't change if you add 2 pi to it and subtract 2 pi. Now it's a difficult problem because if you think about this free energy, it's like energy, right? Why would you say that adding a constant shift to the energy doesn't change the system? Well, it increases its energy, right? So shouldn't it, change this? It shouldn't be noticeable. How can we make that addition of a discrete energy to the system be unnoticeable? And that's the problem that I want to discuss next. And basically, this is a proposed solution to that. So this is a solution that first what needs to be done, and then I'll discuss quickly the proposed solution. So what needs to be done is this. I just already said that we need somehow to compactify the range of f. Make sure that any constant shifts to it by some, I'll call it mu n, is unobservable. It's something that we cannot observe. And if we cannot observe, then we should equate all those f's. We should treat them equally. And if that's the case, then our description, correct description, is not the Mandelung, but the Schrodinger. If we can argue that there may be a constant shift of f that is not observable, then this wouldn't be a correct description. This wouldn't include this unobservability of f. But that would make this correct description, because that's exactly what's needed. Okay, so how can we make this free energy, piece of the free energy, shift in the free energy, unobservable? And as I say here, if that, and again, there are calculations need to be done. I'm skipping those calculations. They're done in the papers on emergent quantumness in neural networks. They are done in the other paper, follow-up paper towards a theory of quantum gravity in neural networks. Again, only the part that deals with quantum mechanics is relevant for our discussions. So you can do that. And intuitively, I already explained you why that happens. Is because we want this shift, 2 pi shift here to be unobservable. But how can we make that shift? And if we do make this shift, then whatever plays the role of h bar in physics, and you may also know that this h bar is what measures the quantumness of a system, right? Now it will be related to that shift. And in this case, if we make this shift unobservable, and mu is the shift, n is the integer, but mu is the shift, then this effective Planck constant will be proportional to this mu. So the larger mu, the larger the shift, the smaller mu, the larger the h bar, the effective Planck constant. The smaller mu, the smaller h bar. And then it's also proportional to 2 pi and epsilon. So, but we need to first argue that this is a possibility. And if that happens, this would be the relevant action. So the action that we had before, this action, we had before here, this action with that shift, NF, an observable shift, can be replaced with this action, and then we are, once we have that action, we are no longer varying with respect to P and F. We'll be varying with respect to psi, which is now has both components, has both P and F. Okay, now that's all great. Again, I put in the box because that's important. It's like if we have that, then we're in business, right? But we don't have that yet. But the bottom line is that if we do have, I'll call it the multivariateness condition. So basically, f is a multivariate function. If we have that, if it is satisfied, then we have a Planck constant, which is described by equation number 3, and the Schrodinger equation is the correct action, is the correct action to describe the system according to the stationary entropy production principle. And then this is the equation that we get. But the main question is how to get this multivariateness condition satisfied, how to make sure that this shift is unobservable. And that's what I'm going to tell you next. And after that, that will be all. This will be the last slide I'm going to show in this lecture. And I will argue that current algorithms do not have that. So what we want to do, we want to implement something with an algorithm such that this is a correct equation, the multivariateness condition is satisfied. And if you do that, then you may have this emergent quantumness all the way. And then not the Mandelung equations, but a Schrodinger equation would give you the correct description. And maybe you can get all the benefits of quantum computing from that. But that's, again, not something that I can prove you now. I'm just showing you what are the possible analytical descriptions of the non-equilibrium systems we can have. One was the Mandelung, and the other one is, as I will argue, the Schrodinger. Okay, so here's our last slide, and it's an important slide because here we will be changing the statistical ensemble. Now, 2 lectures ago, we discussed a statistical ensemble, which I call the canonical ensemble, where the main idea was, let's consider a trainable variable, non-trainable, an ensemble of non-trainable variables, where the average loss function is fixed. And then we use that, we use the maximum entropy principle and derive the distribution, canonical distribution. And that was canonical. Canonical meaning the number of neurons is fixed, but the average, the energy can change, but its average value or loss function can change, but average value is fixed. Now, what we're going to do, we're going to consider a neural network at equilibrium at some temperature. That means that the average value is fixed. So some temperature from the previous 2 lectures. But in addition, we're going to impose one more condition. We're going to assume that it's not alone. It's not just a neural network with a fixed number of neurons, but there is a reservoir, a bath of additional neurons. What does it mean? It means that there is an ability for you within your learning algorithm to increase the number of neurons and decrease it. Increase or decrease by whatever method or algorithm you want to do that, but there is this ability for you to write a code where you are dynamically changing the number of variables. Now, whether you are changing it by yourself, just identifying some bad neurons that are poor performance and remove them, or maybe you're identifying the struggling neurons and then add the neurons to help them. Whether you do it by hand or it happens at the level of dynamics. Again, it's something we discussed in the first few lectures, where it may happen that some neurons become dead and then keep streaming the same output all the time. And then effectively they're gone from the system. All right. And then eventually they may come back and become again alive. And then the number, in this case, the number of alive neurons that are actually doing the learning is not fixed, it changes. So it may be something that you put in your level of algorithm, or maybe something that is already happening in your system because there's like many neurons and not all of them are used all the time. Now, by changing algorithm, you will be changing this quantity. How does the free energy with changes with the number of neurons? So add 1 neurons, would it decrease the loss function or would it increase the loss function? Mu positive or mu negative? Doesn't matter as long as there is this finite shift. Because remember, the df dn is also du dn equals to the du dn is the effect to the loss function from the addition of 1 additional neuron. So here I doing this as if it was a continuous variable, and of course n is a discrete variable, but nevertheless there is some finite shift that comes from adding a single neuron. And in physics, this is called chemical potential. Basically, it tells us how easy it is for a system to get a new particle in the system. Does it like to have new particles, or it wants to, doesn't like new particles, and if you put 1 more in, then its energy goes up. And then you can have different particles, like fermions don't like to cluster, and so you put 1 more, and they're trying to repel it, so their chemical potential for them would be positive. And again, depending on your algorithm, depending on what you do, this in generally this is the right thing to write, and so this mu can be calculated. You can just keep adding and seeing how things change. Now of course, may happen that mu is very large or very small, and then although we do have this condition that I'll argue we'll have by changing mu to be very large or very small, this quantumness may actually break down, because here this condition tells you that this should be true regardless of how many kind of neurons you would add to the system. Now this is not true in general, and in general you actually have mu that also depends on n, and so it's not as simple as this. But if you manage to build a system where mu doesn't depend on n, and so then or at least for some ranges of n, then this system has a chance of being correctly described by the Schrodinger equation, and it has a chance of being approximately quantum. All right, so let's keep going. So yeah, so this is our modification to the system, ability to add and remove neurons. Now, so your ability to increase or decrease the total number of active neurons. Again, active can be understood in two different ways, whether they're really the neurons that are present in your system or the ones that actually doing actively non-trivial calculations. They're not dead. Their output is not just fixed number. Okay, so now if that's correct, then the first law actually should be written this way. And so it's not F that plays the relevant role, but this is called the grand potential has to be 0. And then what you have F is they'll have some fixed number associated to this plus this constant shift. That's what F would be. This is what free energy would be. It would have the what's called the grand potential contribution plus this shifts to the number of neurons. You can now differentiate both sides with respect to n, and you will see that mu is equal to dfdn. So and that, now we're in business. Now all of a sudden we say, all right, so maybe that's what your algorithm is. You have lots of neurons. You don't even know how many neurons there are active and not active. You don't pay close attention because that's your analysis. You're doing a coarse grained analysis, and then the correct description is actually Schrodinger. Okay. So and that makes the whole difference about the two descriptions. Both descriptions are correct, but in a different limits. And one is correct when the number of neurons is fixed. The other one is correct when the number of is not fixed. What's interesting to note is when you make the number of n is unknown, it seems like you complicate your system, and yet the equations become linear, simpler. And this is some some aspects of it that should be appreciated, right? Because quantum mechanics is very simple. It is linear system, mathematically simple. It's easy to calculate. It's completely linear system, but it comes only when you have this addition here, when you make the number of neurons unknown. Okay, so I will probably stop here, take questions, and quickly outline what we're going to do next. So next time we will actually, there are two different directions we can go. One direction is to explore at the level of algorithm what it means the number of neurons not to change. That's one direction that one may take. The other direction is to study how this probability distribution P of Q actually evolves, the one that we've been studying, right? And there are at least 3 or 4 more lectures that we'll go when we'll explore all those different limits and the benefits of all those algorithms to the learning dynamics. But I think the general outline of how we would be treating non-equilibrium dynamics of trainable variables now completed. There are certainly things to do by relaxing assumptions, many simplifying assumptions with that. For example, even here, when we say that this is completely unobservable, regardless of what z is, it will not be the case, because certainly if I make a number of neurons 1,000,000 times bigger, it will be very much noticeable. And so at some point, this condition will break down. And so seeing how the breakdown of this condition to what kind of observable effects it leads is another interesting direction. But let me take questions now.
So by changing number of neurons, you're proposing that's one of the ways to kind of expand the system to be able to approximate a Schrodinger equation.
That's right. That's right.
So it's not the only possible way then.
I don't know. That's kind of the only way. There are lots of unrelated to learning theory. There are lots of articles where people are claiming that they see emergence of quantum mechanics, and I think the usual problem is that what they would show, they wouldn't show Schrodinger equation, they would show you Mandelung equations, and that's not quantum mechanics. So showing where this shift from Mandelung to Schrodinger occurs, as far as I know, this is the only place where we can actually point the finger and say, look, in the Mandelung expression, F, the free energy, played the role of this complex phase. and to make it have a constant shift, something has to change discretely. The other thing, maybe, I mean, again, here I'm just saying the number of neurons. You can take this idea further, right? What are the other discrete things that happen in the system, that are present in the learning system? What are the other things? You may be able to answer this question. And so the number of neurons is discrete. What else is discrete? We need discreteness, but what else is discrete in the learning system?
In layers, but that's
Yeah,
basically
number of layers,
neurons.
number of trainable variables, right? Number of weights. I mean, there's lots of things that can be discrete. The point is that you don't want just it to be discrete. You want mu to be of effectively important size, and also not to change with the number of them. Because if you put here df dl, well, certainly the loss function will be changing dramatically, and this derivative will be changing dramatically. It's not just going to be a constant. Maybe df dk or du dk equivalently, they change in the number of loss function with respect to trainable variables may have the same effect. Now, the problem is then you have to kind of have two types of trainable variables. The ones which I observe, and that's kind of the first, yeah. So then you really need to put some of the non-trainable variables into those hidden variables. And then you will have to say, okay, here's some subset of trainable variables. I observe them and only study dynamics of them. And then there are others, maybe someplace in the bulk, some hidden connections, and I don't study them carefully. I only look at them at the level of statistical ensembles. Now, their numbers can also be discrete, and so if they're discrete, they are good candidates. So any discrete variables are good candidates, but you have to be very careful because you want to make sure that this is a constant. So the FDN or DFDK or DUDK, DUDN, all those things will have to be constant.
And like, what would be like the time scale that you think the neurons should change, or other discrete parameters, trainable parameters
So very
change?
good. Yeah. So by doing that, you're just playing around with this, right? So you're adjusting h bar, and then by making this mu too large, you basically can make this effect. You want to make, we will discuss some of that later, but there are basically conditions that you want to, either you experimentally play with it and see what works best, or you want to make sure that this h bar is kind of the parameter that determines of how quantum the system is. And so there are a few places. So this epsilon here is a time-like parameter on which you are studying the changes of the free energy, and so this is the parameter that has to be long enough so that you can calculate such quantities. But yeah, there's lots of unanswered questions here. I think my main message here is there are those two ways of looking at the non-equilibrium dynamics of the learning system. And we are going to take this one step further. So the next two lectures will be kind of taking this two different ways. One saying, all right, so let's play around and see what happens when the number of neurons change. What do we get from that? And the other directions is let's look at what probability distribution of Q changes. And they are kind of two different ways of looking at the system, but yeah, there's lots more work needs to be done to completely settle all those issues. Lots of open questions here.
Yeah, this is very interesting from the side of neuroscience also, because we know that the brain produces new neurons and recycles them all the time, including connections. So
absolutely. Good.
That's very thanks.
Yeah, thanks. Yeah, absolutely. No. It was actually motivated by the neuroscience, like neurogenesis. Neurodegeneration happens all the time. Now, in biology, we've discussed this in our papers on the modeling evolutionary biology using learning in the same way. All those things are extremely important for the evolution. And so if this mu becomes very large, and adding one more trainable parameters becomes very expensive for the learning system. It just stops learning, and then it becomes inefficient. So making mu very large, and that's, we kind of see it in biology. We have examples of systems that just stopped evolving because of exactly that. They are not able to add new trainable variables. But yeah, it has a connection to both physics, biology, and who knows what else. Other questions?
Instead of changing the free energy to be multi-valued, can you have changed the measurement theory instead? Is it something that can be changed?
it's a good question, but the answer is no, because let's go back to this, right? We're not even at measurement, all right? We're not even here yet. Even at the evolution, like without measurement, we wouldn't have a correct evolution of our system if psi was not a legitimate complex number, right? So we would be now in measurements, of course, psi plays a major role, but you cannot go away from the Schrodinger equation. Now, of course, it may be possible. So we only discussed two ways of looking at the non-equilibrium learning dynamics: the Mandelung way and the Schrodinger way. Now, there may be other ways, of course. Here, the reason we did those two ways is because we know how to do mathematics, right? Maybe you can do other approximations, analysis, and maybe, and maybe that will give you some other dynamics, which neither classical nor quantum, and then you will see, all right, so that's the right way of describing how the system evolves in certain limits. And maybe there the measurements would play a more important role, and then by tweaking around and changing the measurements, you can, so, but for now, only two, so maybe more,
Okay, thank you.
Sure. Other questions? All right, so very well. Let me now stop the recording. Thank you, everyone.